There we go. Good evening. That's louder than I was expecting. My name is Rob Hamilton from Foundations in Genesis in Idaho. We bring in creation speakers from around the country 6 times a year in this area. Tonight we have Skipper Kagamaster. I just slaughtered that. He's a former student and a researcher in physics. He is passionate about the interplay between God and science and God's Word. He has a PhD in physics, and his focus is in high-energy nuclear physics. So he has a pretty good background. And with that, I'll give you Skipper.
We'll see. Yeah, my switch is okay. There we go. There we go. There we go. And then, do you mind queuing up the first slide on there? And I'll just tell you a little bit about myself. Thank you for the introduction. Thanks all for being here. Again, my name is Skipper Kagamaster, and a little bit about me. I kind of started off as I guess what you would call a theistic evolutionist when I was younger. I was raised in secular schools and Navy schools, and Big Bang cosmology, evolutionary theory was what was taught, and I thought, okay, well, maybe God somehow did this as well. And as I became a more serious student of my Bible, I started to have major issues reconciling what was said in the Bible and what I was being taught from the sciences. I had some friends that led me toward the creationist path, and that helped to really reconcile a lot of things in my mind, but I didn't pursue it outright. I started off in university doing biochem, and I was a really very disinterested student. Didn't do a great job at most of the things I did, and finished up with a bachelor's degree in English. And then fast forward several years, I always felt this nagging pull back toward the sciences. Went back as a very dedicated student and finished my second bachelor's in physics, my master's, and then earned my PhD in physics doing high energy nuclear physics. Just it's like particle collisions, but with larger sets, so using atomic nuclei instead of particles. If any of you are having trouble sleeping, you can ask me about my research, and I'll be happy to cure that for you. But during the course of that, I had a lot of things that were not well reconciled in my mind that were said by this kind of monolith of science and didn't reconcile with the Bible. And it was something that was honestly a little scary going into delving all the way into physics like that, to say, am I going to be really challenged here? Is this something that's going to be really difficult for faith? And I found the opposite scenario. I found the more that I studied physics, to kind of paraphrase Einstein, the more I study physics, the more I believe in God. So what I'd like to do tonight is share with you one aspect of that. There are a lot, but one as it relates to the Big Bang. And so this is my impressions from the vantage point that I've been blessed to have, and hopefully there will be some impressions for you on there. Now, I'll show you where we're going. I will forewarn, it might get a little technical in places, but I do promise, if I lose you, I will pick you back up. All right, we're going to come back around. So if you get something and you say, hey, that doesn't make any sense, I didn't quite get that, please feel free to ask. I'm happy to explain anything, but we'll come back around to it. So here's where we're going to go today. First, we're going to start off with what I call the big claim. What is claimed by Big Bang cosmology proponents? And then I want to talk about just kind of in general what a model is. Those of you who are already involved in the sciences, this may be something that you've already seen, but I think that it's not something that's well understood by the general public, and further, I think it's something that's even not well practiced by scientists at large. What a model is and what a model isn't. And then once we're armed with that, we can then look at some of the specifics of the Big Bang. And then I want to briefly go over kind of, is there a compatibility with the Big Bang in the Bible? And then we're going to pull back a little bit to conclude with some expectations and evidence. Intuition is actually a very good guide. The greatest scientists of all time, actually two of what I'd say the most formative revolutionary scientists, being Isaac Newton and Albert Einstein, were both often led by an intuition. And many of the great scientists had just a dogged intuition where they would say, this is what I think should happen. This is the way I think things should be, and they pursued that as a lifetime work and changed the world. So we're in good company as we look at that. So without further ado, let's get into it. So the claims of the Big Bang are also pretty big, no pun intended there. But one of the things is the scientific claims. So proponents of the Big Bang will often say, this is just what the evidence shows us. You can see from observational sciences demanded, astronomy, particle physics, heavy ion physics, other disciplines as well. What the claim is, we look out into the cosmos and this is what we see. So don't blame us, this is just the way that it is, and we're showing you that way, and you can accept it or not accept it, that's on you. Also, the other claim, I've always found this very curious as I started to learn more about it, is this specificity. We know exactly how it worked. Not only can we see it, but we can see it so well that we can get specific down to a time increment like 10 to the minus 43 seconds. Now, if you don't know what that means, I will flesh that out for you. If you do know what that means, that it's a really ridiculously small time increment, and we'll talk about what that is and how they can say that. And here's some quotes just to kind of back that up. We have the late Stephen Hawking saying God may exist, but science can explain the universe without the need for a creator. And that's one of the bold statements. This is saying we have it, we've solved it. We look out and we see it. And then as written in Forbes, another physicist, Ethan Siegel, had said, for more than 50 years we've had definitive scientific evidence that our universe began with the Big Bang. Okay, so this is saying this is incontrovertible. Now, on the flip side of it, we have some biblical scholars, most notably Hugh Ross and his outfit here, Reasons to Believe, even back as far as 20 years ago, saying, Big Bang, the Bible taught it first. So it's this idea of you can find the Big Bang, by the way, in the Bible. Not only is it not incompatible with Big Bang Theory, but Big Bang Theory comes right out of it. Now, these should be things that we take seriously. These are serious claims. If we are Christians, and I believe that science is the study of general revelation, and all good science has come generally from Christians. You know, if you look at the history of science, it was people saying we should be able to observe the creation and see the fingerprint of God in it. If the Bible teaches the Big Bang, and if the evidence demands the Big Bang, we should all be Big Bang cosmologists. If that's what is true, if that is a proper exegesis of Scripture, if that is a proper view of science. All right, so that's what we're going to be looking at tonight. But before we do, the Big Bang is a model. So I want to talk about what is a model. What does that even mean? Because sometimes a model can be seen as something you can just toss and dismiss and not think of, or is it, no, this is ironclad. You'll often hear people say, well, look, you don't want to believe in evolution or the Big Bang. Well, hey, gravity's just a theory too. Why don't you try walking off a building and seeing what happens? I've had people say that to me. And they're conflating terms here. So I want to be specific with the way that we treat these sort of things. So Johannes Kepler, this is the guy that came up with all the laws of planetary motion. If you're familiar with those, like the planets orbit the sun as an ellipse with the sun at one of the foci of the ellipses. This is something that Johannes Kepler came up with through very painstaking review of all of the material that they found. So it wasn't a mathematical treatise. It wasn't actually so much a model. It was just, that's what he observed, which is very interesting. And he said the chief aim of all investigations of the external world should be to discover the rational order and harmony which has been imposed on it by God and which he revealed to us in the language of mathematics. So understanding mathematics as a language. Now, some of you understand mathematics as a language, but I think many of you probably, like me, when you were learning math, you were taught incorrectly. You were taught mathematics as a toolkit full of clever tricks and algorithmic processing to get you from a starting point to an answer. And that is not what mathematics should be. If you want to do that, take your phone, it's got a calculator on it, use that, you will get the right answer every time. If you want to get the right answer, that's the way to do it. I know it's a little sacrilege for me to say use a calculator, but if you're doing calculation, use a calculator. Math speaks as a language. Math is the way that we say things precisely, and the way that we can logic those things that we say precisely to come up with new things. So what does that look like? I can give you a kind of a simple example just to kind of set the stage for that, and then we're going to actually look at a physical model that's a classical physics model. So let's say you've got this, a bushel of apples, and you have 8 apples in there. And now let's say that I have several bushels of apples. I can say that in English pretty succinctly. I can say 4 bushels, each containing 8 apples, equates to 32 apples. How would I say that in math? Yeah, 8 times 4 equals 32, right? We haven't gained much here because we're not saying much, but this is how you'd say it in math succinctly. Well, what if I now change this scenario to something still a very simple system, but slightly more complicated? I have a certain number of bushels of apples. And each bushel contains a certain number of apples. This starts to get a little complicated if we say it in English. And then if I want to do things to it, like say, well, what if I have half? What if I have double? What if this starts to become very complicated. But in math, to say this statement is very, very easy. We can just say x times y equals z. X is our number of bushels, y is the apples per bushel, and that's what we get. So this is kind of a simple way to do this. So to get your feet wet if you're not used to thinking of math as a language. And then in my opinion, the greatest scientist to live, Sir Isaac Newton, he says God created everything by number, weight, and measure. And what he means by this is, I kind of love this outlook. Mathematics is language. Mathematics is information. How did God create? In a lot of creation mythologies, you'll see that their depiction, of Kronos or whoever it is that's doing the creation, takes existent stuff and rearranges it. That's not how the Bible says God created. The Bible says God created by speaking. All right, he spoke and it was so. Now, he can create from his created things as well, if he so pleases, such as the creation of Adam. But the majority of creation was done by speaking. This was a transference of information into the universe. And so what Newton's saying here is we can discover some of the information from the language God spoke by looking into mathematics. That models give us kind of a picture of that, which I think is a really beautiful thing. It's a great way to study anything physical. So first let's talk about what a model is and what a model isn't. This is not an exhaustive or comprehensive list. This is just impressions that I have of things that a good model has, and some things I'll show you the good model does not have. A way to describe physical phenomenon with math. All right, someone once said science without math isn't science, and I very much agree with that. Like Ernest Rutherford, he said, what is it, all science is either physics or stamp collecting? I agree with that too, but it's not as nice. But you should have some math in your model. If you don't have math, you're not describing things exactly enough. A working understanding of how a physical phenomenon acts and interacts. Okay, so again, this is something saying we have an idea of how things work and we can describe it. A group of axioms and then derivations based on physical observation. So an axiom may be a new term. Some of you, that's old hat. But if you've ever heard the term premise or presupposition, that's the same thing as an axiom. And math will generally say axiom instead of presupposition. What it is it's a statement that we take as true without proof. Now, before any of you think, aha, but I don't take anything as true without proof. I need proof for everything. No, you don't. That's not true. And not to be dismissive, but there's no way to do anything without having some axioms. There's mathematics has shown, there's some great mathematicians out there who have some cool proofs on this. You cannot have a self-referential system, which means it refers to nothing outside, only itself. We have to have starting points. So a model will have axioms and then derivations, so logic that we can do on those, logical type operators, which in mathematics is going like this familiar, plus, minus, etc. When you get into higher dimensional spaces, it starts to get a little more complicated, but you still have these rules that you use. And hopefully, if you have a good model, you'll come up with something new using your starting good axioms and derivations. Prescriptive, descriptive, or both. Okay, so there are different types of models. A prescriptive model is a model that comports with reality, but doesn't necessarily describe reality. In physics, we see this a lot because we'll do things where we'll say, hey, let's do a limiting case here. Let's say that, we like to do this a lot. Well, how far away is that object? Let's say it's infinity away. Okay, well, that's something that we can then do some calculus on, and we can maybe get something that comports with reality, but we don't actually think the thing is infinity away. But sometimes they can be descriptive. Sometimes there will be models that people might say, we believe that this reflects actual reality. One of the big ones for today is quantum mechanics and quantum field theory. Most people believe that it describes accurately how reality actually works. I personally don't agree with that, but there are models that can be descriptive. And a basis for simulation, in a lot of my graduate work, we did simulation with particle collisions. And basically what you have is all of the math. You can put it into a simulation, and you should be able to have that simulation produce something that looks like what we see in the real world, if the model is any good at all. Okay, so that's some things of what a model is. Just kind of get your head wrapped around when you hear the word model, what do you think? What isn't a model? This is a big one, the truth of the universe. Even if you have a descriptive model, that doesn't mean that it's true. So even if you take something and you say, this is the way that we think it works, that doesn't mean that this is what nature showed us, this is what it actually is. Okay, it's still just a model. It's also not data or observation. You can't say we observed a thing and here's the math that came out of it. You can say here's our mathematics and it goes along with the thing we observed. And I'll show you what that looks like in a second here. But it's also not, and let's not be dismissive, it's not just an idea. It's rather more than that. A model should be rather more than just, hey, I have an idea. So for gravity, you can't say, well, I think things get pulled down toward the center of the Earth. That was Newton's first idea. But that's just an idea. That's not a model yet, until you put something to it that has some mechanics that shows how that actually works, that makes some predictions, that has some value that way. So what does this look like in practice? Well, we're going to go with a spring model, and I'm going to walk you through how a physicist looks at a spring model and how they can come up with an equation of motion from this. Like I said, if you get dropped, you'll get picked back up. Any of you ever go on the Jungle Cruise ride at Disneyland? And you have guides, right? And what are the guides called that make sure you're not going to get hit by headhunters and all this sort of thing? I remember because they're called skippers. So of course I remember that. So I will be your skipper, guiding you through this mathematics, and I will make sure that none of it bites. So if you have a spring, springs are springy. You pull the spring, you put a weight on the spring, it's going to stretch. If you put twice the weight on the spring, which we have here, and it stretches twice as much, we can say there's a linear relationship. And that would give us something that looks kind of like this. We have this K, which describes the springiness of it, and that's going to be a constant. You can get more complicated than that, and people do, but we're not going to here. So this is what it looks like when we have a model. Here's a model of the spring mass system, okay? I think math is beautiful, so I wanted to make sure I showed a little bit of math tonight, but I'm going to walk through what all these mean. Don't worry, we're not going to do any calculus. It was already done for you. But this is using a model with some axioms. One of the axioms, we start with this first guy here. This is a way of arranging statements of energy, and our axiom is going to be twofold. One, we agree with Newtonian mechanics. This is, for anyone who's interested, this is called Lagrangian formalism, but this uses Newton's laws, basically. So we're going to take Newton's laws, that's one of our axioms. And our other axiom that we're going to use is that water goes downhill. Basically, that energy follows the path of least resistance. With light, this would be called light follows the path of least time. All right, so in this particular one, we're just going to say we want to minimize the energy. That's our axiom. We're not going to prove that because that's our starting point. So those are our two starting points. And from there, we can say, okay, well, let's arrange the energies. What energies do we have in this spring system? Well, we have movement energy, kinetic energy. That's a term for kinetic energy. And then we have spring energy. We have the potential energy that's in the spring. So we have those two energies. Okay, now we have that. Now we got to go to the next step. Now we're going to minimize it. We're now doing some mathematics on our axiom of energy is minimized, takes the path of least resistance. So this d over dt, that's not division, that's a calculus term, and that means how does it change with respect to the coordinate t, which is time. So we say, okay, we've got one thing that changes with time. And x is distance. It's just displacement in space. How does it change in space? And that makes sense. If I'm moving in time and space. So we're going to minimize with respect to time, minimize with respect to space. And when we do the math, when we do the actual calculus, we come up with this little equation here. Now this is where Newton comes back in. This little term on the left is a force term. Mass times acceleration, that's all that says. So it says we have a force, and the force is related to this parameter for the spring. Great, that makes sense. Well, now we're going to do what's called solve this equation for the equation of motion. That's what we want. We want an equation that says, how does it move? That's what our model should give us. The good model should give us something how it moves, and we're going to have this equation as now emergent, because you remember the axioms that we put in. We didn't put in any axioms about how does a spring move. We just put things in that said, well, energy is minimized, and Newton's laws we're going to take as valid. Those were our axioms. So what we end up with is this equation here once we solve this guy, and this is our equation of motion, how it moves. All that means x is just distance, displacement, and t is a time. You give me a time, I'll tell you where it is. You say, okay, I want 28.3 seconds from now, I want 80 billion years from now. Fine, we'll put it into here, we'll turn the crank and see what comes out. Well, what's the equation? Well, it's a wave function. You remember cosine from your time in doing geometry is this guy that goes like this, right? So what is this saying? This emerged. We call this something emergent in this little model that we've done here. This emerged, and a wave equation emerged. Well, does this comport with reality? This is what it says. It says, if you displace the spring with a mass, it's going to do what? Back and forth, back and forth, back and forth. This is a good model because that's what springs do. So we like this model. And if we treat it simply like we do here, we have no frictional losses, we have no air resistance, no heat loss in the spring. How long will it do this? Forever, forever and ever and ever. Till the Lord returns. It's going to go like this. But friction exists, so it actually won't do that. But this just to give you a little picture, this is all the math that we're going to do, what a model looks like. So when you have that in your head for a good model, that's what a good model looks like. So good models and bad models. All right, what does a good model look like? Well, it has axioms that make physical sense. They should be motivated by the physical world. The modeling follows, again, known physical laws. All right, so we're going to take any mathematical proof, you're going to take something known, and your proof is when you get to the thing that you were trying to prove. All right, so you start off with things that you know, and the biggest thing, congruent with experiment or observation. If you have a good model, it should comport with what you see in reality. What is a bad model? We're going to have the opposite. Axioms aren't based in reality. Something like this might be, one that fits all of these is something like many worlds hypothesis, landscape hypothesis, sometimes called multiverse theory. There are all these other universes out there that we cannot see or touch or feel or interact with, but trust me, they exist. It's a fun idea for Marvel movies and such, but it's just not something that I would call a scientific model. Axioms aren't based in reality. Model follows your desired conclusion. So let's say we started the model by saying, okay, we're going to start off with a wave equation. That's how we're going to start our model. It's like, okay. I mean, you might get a good prescriptive model for a spring system, but you're kind of putting the cart before the horse when you do that. If it emerges, hey, now you got some legs to this thing. But if you start off with the conclusion, not so great. And then the worst thing a model can be is not testable. And the second worst thing it can be is not in concert with observation. The late Richard Feynman, the premier physicist of the 20th century, he said, it doesn't matter how beautiful your model is, it doesn't matter how smart you are, if it doesn't agree with experiment, it's wrong. And that should be how we always feel if we're doing science, is always should be a reality check. And contrarily, if it does agree with experiment, that doesn't mean that it's right. It just means that it's not wrong. So here's another model. We are not going to do any math on this. This is the standard model of particle physics. This is everything that we know about the forces and the particles in all of the universe except, does anyone know what's not included on here? Gravity. There's no gravity in this model. This model says, okay, without gravity, and the reason is this is what's called a quantum model. It's a quantum field model. There's no quantum theory for gravity. They've been working on that for about 100 years, and nobody can find a quantum theory for gravity. Some physicists contend there is no quantum theory for gravity. They're going to keep plugging away at it as long as we keep giving them grant money for it. There's a little L right here, just like our L that we had, but there are rather more terms. So this is one of the longest Lagrangians that you'll ever see. That's what that L is called. So this is the energy statement about all these guys here, and these are all the particles that everything is made up of. You probably recognize this little guy here, the electron, and there's a bunch of other stuff too. And if you have any questions on that, I'm happy to answer it, but I'm not going to get into it here. But just so you know, this is like what a good science model looks like. And to show you what you can have in reality to say, hey, does this comport with reality? These are some graphs that I made from some high energy collision data. This one in particular here, we have mass right here, and then we have momentum here. And you see that we have these areas where you have a lot of things going on in one spot. And these correspond to particles in the standard theory. So standard model would say these are protons, these are antiprotons, these are kaons, these are pions. So this is a hallmark of a good model. It says some things that are falsifiable. We can test it, and we can do some experiment that seems to give some credence to it. Now, that said, we'll go back to Einstein here. He says as far as the laws of mathematics refer to reality, they're not certain. And as far as they're certain, they do not refer to reality. All that he's saying here is basically you still take it with a grain of salt. Even if you have a great model and it works well physically, science is replete with a history of models being overturned, being falsified, being expanded. So a model is, even a good model, you can't say, well, now we know everything. Now we've got it all nailed because we've got a model. You still have to keep that little bit of doubt in the back of your mind. Healthy science is a skeptical science, right? Anything that you see that comes out of just science, you should take with a little skepticism. And creationists do this often. If some of you are familiar with canopy theory that was in vogue maybe 20, 30 years ago, and that's been left by the wayside because there's some evidence that counterindicated it. That's what you should be doing in science. Okay, that's a model. So we're all done there. I hope everyone has kind of a picture in their mind of what is a model, and now we're going to look at a particular model and some of the claims that it makes and see, do they comport with what we see? That particular model being the Big Bang. This is what we would call, non-pejoratively, the naive picture of the Big Bang. We use that term in physics a lot, the naive picture, to mean kind of like, what would your first guess be, or what would your back of the napkin approximation be? So the way that it goes is, as you may know, Hubble in the early 20th century was looking out into the sky, and this is, I don't know if you know this, but we've only known about galaxies for about 100 years. We didn't know these things were galaxies. They were just kind of smudges out there, and they were thought to be nebula. This was like kind of a gas cloud. Andromeda was thought to be that. We got better and better optics, and suddenly it was like, oh no, that's not a smudge, that's several billion stars, which is really amazing. And there were certain objects in the night sky that were of a type that were expected to have a particular color for their output. And when Hubble would look at these, and when they would do distance measurements, he would find things that are farther away by a particular distance measurement don't have the right color. They're shifted into the red. This is what redshift is. One possible explanation for that is, well, the universe may be expanding. And the farther away something is from us, the greater the level of expansion, therefore the greater level of redshift. That's one possible explanation for it. Now, if you have that explanation, you say, okay, a second ago the universe was this big, and now it's this big. Oh, now it's this big. And so it stands to reason to say, well, why don't we just work backwards? And if we work backwards, we start here, and we'll get down to a point. And that's probably how most of you have heard the Big Bang Theory postulated, is that it's essentially you start at this point, nigh singularity or singularity, the smallest point you can get, and it expands out from there. But that's not quite the actual picture. The actual picture of the common formulation for the theory is somewhat more nuanced, and it works on these things called epochs. Any of you ever heard of this, epochs for the Big Bang? It's not something that usually you have covered, and this was something that when I first learned of, it was very eye-opening for me, so hopefully we'll have some eyes open tonight as well. Epochs mean that there were certain periods of time that were dominated by a particular physics, meaning certain laws were dominant during that time, certain particle types were dominant during that time. So you start off with this Planck epoch, and now I'm going to get into this number. It lasted until 10 to the minus 43 seconds. What's minus 43 seconds? What does that mean? Well, if I have 1 second, I just have 1 second. If I have 0.1 seconds, that's 10 to the minus 1 seconds. If I have 0.01 seconds, I'm now 2 places in from the decimal. That's 10 to the minus 2 seconds. 0.001, I'm 10 to the minus 3 seconds. I'm not going to go all the way to 10 to the minus 43 because that would be the rest of the talk. But you can see this is just an inescapably tiny little piece of time. To show you how tiny this piece of time is, you know, 0.4201 second, it's that amount of time. Scientists generally, the lowest amount of time that they will deal with in experiment is around 10 to the minus 15 seconds, which is really quick. The most stuff I did was around picosecond would be the lowest, that would be 10 to the minus 12, right? The 10 to the minus 43 is so far beyond, I think the lowest that's ever even been measured. Just an experiment designed to measure the quickest speed of time you could is around 10 to the minus 20, somewhere around there. So this is just an unbelievably small little piece of time. It's very specific, right? Why isn't it 10 to the minus 44? Why isn't it 5 times 10 to the minus 43? I'll tell you why in a second. Then after that, you have the grand unification epoch. Still, we're at these really tiny beats of time. 10 to the minus 36, inflation, 10 to the minus 33. Okay, lecture week, now we're starting to get, and that's a picosecond. We do those. We do those in the lab all the time. And then by the time we're at the hadron epoch, that's after 1 second. I think we're all pretty cool with 1 second. And then eventually things go on, and you have, you know, dogs and cars and galaxies and such. So that's more of the picture of it. But what I want to focus in on here is the first 3 epochs and how those look. Because if you don't have a beginning, you don't have a middle, and you don't have an ending. So let's look at the foundations. So the first one is this Planck epoch, and I put this picture up here for a reason. Keep in mind, remember this standard model of particle physics. This is the first instant of the Big Bang. Now, the time is not something that was measured. This is not something that's emergent from the theory or anything like that. This is actually what the time comes from. It's called a unit analysis. We have these 3 guys here. Does anyone know what this G might be? Gravity. That's Newton's gravitational constant. So this is the constant that kind of governs Newtonian dynamics. What about the H bar? This is the Planck constant, reduced Planck constant. And the Planck constant is what makes quantum mechanics. If h is equal to 0, you don't have quantum mechanics. And then the c down here, what's that guy? Speed of light, very good. And speed of light governs which? Well, that's a question that would take a long time to answer. Yeah, but the speed of light is what governs relativity. So if we take the major constants from the major areas of physics, Newtonian physics, quantum mechanics, and relativity, and we put them together in this way with the square root over the c to the fifth, we get a unit of time. We get the units of time, meters per second. And it will give us this Planck time, which is 10 to the minus 43 seconds. Sorry, to give us unit of time, seconds, meters per second is velocity. It'll give us a measure of time if we put these together. This is just from straight up unit analysis. So this does not come out of the theory. This is something that physicists, there's a thought out there that these Planck times are fundamental. Like you can't have half a Planck time. You can only have units of Planck time. And so they're trying to quantize time is what it is. Quantize just means you make them discrete. They're in little buckets and you can't make the buckets any smaller. So these Planck times are what we have as the onus behind this 10 to the minus 43. And this requires, this Planck epoch is dominated by what's called a TOE, a theory of everything, if you've ever heard that. What's a theory of everything? It's everything you see here plus quantum gravity. It's dominated by quantum gravity. So the Planck epoch, the physics of the Planck epoch is mainly quantum gravity. Do you remember what we said is not present in the standard model of particle physics? Gravity. Quantum gravity, because we can't quantize it. What this means is the known laws of physics as we know them today do not apply to the Planck epoch. There are a lot of theories about this that have come and gone over the last 60 or so years. None of them have had any legs. We do not have quantum gravity. So we don't actually have any physics for this. As a model, there's nothing here. Okay, well, let's do the next one. So much for that one. Let's go to the grand unification epoch. This is a gut, grand unification theory. So we've got toes and guts here. Grand unification epoch, just after the Planck epoch, and now we have different forces. You've all heard, I'm sure, of the electromagnetic force. If you have two protons, they're both positively charged. If you get them close together, they should want to fly apart, right? But what's the nucleus made of? A bunch of protons and neutrons. All these protons packed together. Now, let me show you how, I apologize, how unimaginative physicists can sometimes be. They say, okay, well, if they all should be flying apart really fast, there must be another force, and that other force holding them together must be really strong. What do we call it? The strong force. Okay. And there are force carrier particles for this that they say kind of glue everything together. And we're physicists, we put on at the end of everything. Electron. Well, what's the particle that does electricity? The electron. Okay, what's the particle that does the strong force? The gluon. Okay. The only thing imaginative really is quarks, and physicists didn't come up with that name. But what this is saying is during this time, this grand unification epoch, all of the forces that are part of the standard model, strong, weak, and electromagnetic forces, were all one force. Now, there's good science to show that the weak and the electromagnetic force, called the electroweak force, can be the same force at high enough energies. I think there's some good evidence for that. I'm not going to say that's what nature is, but I think there's some good evidence for that. But there's nothing for the strong force. And that's been looked at for, again, decades. Some of the smartest people have gotten together in large collaborations, spending an irresponsible amount of government money to try to find this grand unification theory, and they cannot find it. So another way of saying that is, again, in this particular epoch, the known laws of physics do not apply. Now, don't misunderstand me. I'm not saying no one will ever make a grand unification theory. I don't know. Maybe someone will come up with something cool. I kind of hope so. I like that. I like when physics can delve into new territories and come up with new things. But it doesn't exist. So if someone is telling you this is just what we see, that's not strictly speaking true, at least not for the Planck epoch and the grand unification epoch. Okay, well, let's move on to the last epoch we're going to look at here, the inflationary epoch. This is just after grand unification. Now remember, I said that kind of picture where it starts big and just gets smaller, smaller, smaller back down to a point because we back extrapolate the expansion. You expand backwards, you shrink, right? That makes sense. That's not what it actually looks like. It actually looks like this curve here. And if you see this, it sweeps down and then comes back, right? We have this really, really high area of expansion. And this is the idea behind inflation. This is actually how Big Bang cosmology is formulated at present day and has been for, I want to say about 40 years, somewhere around there. They've had this idea of inflation. I think that might have been since the 70s. This is necessary for the Big Bang to result in our universe. The problem is, and this is one of the problems that inflation is meant to address, the problem is if you start small and you start expanding slowly, everything mixes. Let's say that you take a pot of boiling water and you throw bouillon into it and you stir it around. What are you going to get? Yeah, you can get broth, right? It's just going to be broth. Now, if you ladle from one side versus from another side, will there be any difference? It's going to be the same. If you've mixed it well enough and long enough, it's going to be the same thing. And that's the problem if you have a slow rate of expansion. If you have a slow rate of expansion, everything mixes, everything homogenizes, and you get nothing. Nothing coalesces, you don't have galaxies, you don't have stars, you don't have cats, you don't have anything. Okay, so we need a slower, or a faster expansion. Well, here's the problem. If you have a fast expansion, nothing communicates. Nothing interacts. This is my biggest problem with something like multiverse theory. We can't interact with it. If you can't, physically, if you have no interaction with something, that's a good way of saying it physically does not exist. And if you had a universe with too fast of an expansion, you might have a particle all by itself. The universe would just be, a neutrino or a photon or something like that. And that's it. Because it doesn't interact with anything. Things would separate too fast. They wouldn't be able to have any signals go back and forth. So you need both. And that's the problem. You need to have both. So the theory goes this way. At this 10 to the minus 36, expansion accelerates just crazy rapidly. This huge amount of expansion that happens in a very small amount of time. So the rates here, 10 to the 56 to the 64th, all these, it's the same thing but in the other way as 10 to the minus 43rd that we looked at. If I have 100, that's a 1 with 2 zeros, right? That's 10 to the second, 10 to the 2. So this, we're talking about expansion rates per second of 10 to the 55 zeros, 64 zeros. Huge expansion rate. To give you an idea, in this tiny amount of time, 10 to the minus 34 seconds. Now remember, we can only measure down to 10 to the minus 20th. This is many, many orders of magnitude lower than any scientist could ever measure. In that amount of time, it would be like taking a golf ball and having it become 45 times the size of the known universe. So this was rapid expansion. Okay, well, why do we say that it does that? Well, the problem with this is, you remember when we did our model, and we had our spring equation, and we had all of our axioms, and then we had an emergent equation of motion. It emerged. It came out of the mathematics. We had this wave equation. Well, the problem with inflation is it's non-emergent. Oh no, when this got converted, everything blended there. Well, to fix that, it's non-emergent, and the known laws of physics, therefore, again, don't apply. There's no physics known to have a mechanism for this. This is an insane amount of inflation. This is something where we were going slowly and then suddenly went really fast and then slowed down, because if we kept going fast, we wouldn't see anything, right? If we kept going slow, there'd be nothing to grow, there'd be nothing to make. So we fix it by doing this. Well, here's the problem with this. This is just a goalpost move, right? That's all that we've done here. We said, hey, there's a huge problem with the Big Bang. This doesn't seem to work. What if inflation happened? What if it started expanding really, really quickly for no reason, and then it stopped expanding really, really quickly for no reason? And one physicist puts it this way: down-to-earth astronomers are not convinced that inflation is a useful model. It moves the problem to earlier times. It does not solve it. This would be like I'm sitting at my desk working, and I suddenly realize, hey, my feet are wet. I didn't go walk in the snow. There's no water break in here. It's not raining inside my office. Why are my feet wet? And a scientist comes over and says, aha, I figured it out. I know why your feet are wet. Your shoes are wet. Okay, why are my shoes wet? You have the same question, you just pawned it off to something else. And that's what inflation does. Inflation, many will say, solves all of the problems of the Big Bang. That's not strictly speaking true, but these problems, some of the problems we're looking at here, okay, they can be solved if we have inflation, and if we have a grand unification theory, and if we then go further than that and we have a theory of everything. That solves some of these fundamental problems of the Big Bang. And I will concede that it absolutely does. The problem is, now we have the problem of, well, how did inflation occur? How do you have a grand unification theory? How do you have a theory of everything? It just pawns the problem off to another space and says these are just open questions, and once we solve these specifics, well, then we'll have it in the bag. Well, and I'll say exactly this. You're shifting the goalpost. Well, so much for the science of it, but let's look at the Bible, because we're people of the book, right? If the Bible teaches the Big Bang, even if the evidence doesn't show it, we should at least find Big Bang cosmology to be fairly compelling, because we should go with what the Bible says. And some are claiming, as we saw, that the Bible teaches the Big Bang. So let's take a look at that claim. First off, and you can look at this while I'm talking, I'll go through some of these briefly, but the Bible clearly does not teach the Big Bang explicitly. I think we can all agree to that. There's nothing in the Bible that says, in the beginning, there is a singularity in the fabric of space-time with quantum fluctuations, and then the singularity expanded for a little bit, and then it expanded a lot, and then it stopped doing that, didn't want to do that anymore, and then it expanded some more, and then we had galaxies. It doesn't say that. So you can't say that the Bible teaches it explicitly. So what you're left with, and this is what I used to believe, was that the Bible's an allegory, that the days of the Bible correspond to maybe these epochs, maybe some other periods of time, that they don't actually mean day. I'm sure you've heard this. Does day mean day? Are you sure day means day? Sometimes day doesn't mean day, right? And so you're left with making it an allegory. Well, here's the problem with that. When we look at the order of events, in the initial portion of Genesis here, we have the first day 1 to 2, we have the earth. And then we don't even have the sun until day 4. So looking at that, and you can look at some of the other ones on here, this is, I believe, an AIG graphic, pretty well done graphic. The orders don't match up. So we started with, okay, Genesis is the Word of God. Maybe it's an allegory. Maybe it was an allegory. Well, nothing matches. If you have an allegory, you have to say what corresponds to the thing in reality that it's allegorizing. You have to have something it symbolizes, right? You have to be able to match those things up. You should be able to draw me a chart. Day 1 corresponds to this beginning portion. Day 2 to this beginning portion. If you're going to say that it teaches the Big Bang, well, the allegory doesn't work at all. So what are we left with? If the Bible's not history, and if the Bible's not allegory, then it just becomes mythology. And that's where this leads. Now, is it mythology? Here's a great study that was done. This was done by Stephen Boyd. There are a lot of studies on trying to find what's called the genre of literature for Genesis, but this one's the best because it has a cool graph. And, if you don't have a graph, what are you even doing? So he looked and said, okay, let's try to see what Genesis falls into. And he had 2 categories here. He had a binary, poetry or narrative. Now, this doesn't mean like a poetic narrative. He meant by poetry something like, something from the Psalms that's not meant to be taken as like literal historical. And something that was narrative would be something taken, maybe from like 1 Samuel, something that is clearly meant to be historical. And said, okay, I can take a couple of, and this is a model, by the way, so we're seeing a model played out in real time here. So I can take this ratio of preterites to total finite verbs. It's just a way that the verbs are conjugated, the way that the authors put the language together in those particular passages. He said, well, I can kind of count these verbs up, and I can put them in a scenario where I can make this interesting curve. And this curve has a steep drop-off. It has a top and a bottom, and then a little uncertainty portion here. And this is a classification curve. This is something that looks like, you may have heard of like a step function for any of you who are into mathematics. It's kind of like that. And what they have is, okay, here's the poetic passages down here that are undisputed as poetry. And this model is putting them all over to the side here, except for one. It is a model, right? It's not going to be perfect, because models aren't perfect. And the narratives it puts up here with, again, we got this one little outlier out here doing his own thing. So it's not a perfect model, but it seems to be, I would say this is a pretty decent model. This seems to classify things about where we would expect them to be. And where does it put Genesis? Well, that's this blue triangle right here. Genesis, it puts it firmly in the realm of historical narrative. Now, like I said, there are other word studies, there are other hermeneutical studies that come to this same conclusion as well. And I believe this is the best place to put Genesis, is historical narrative. I believe that the Lord was telling us, here's what I did. The foundation of the world is kind of a big deal, something we would like to know. And God did not leave us ignorant in that. But what does this all really come down to? Does day actually mean day? Is this history? Is this narrative? What does it really, really come down to? And I would submit that it comes down to this. Did God actually say? Did he actually say day? Did he really say 6 days? I mean, there wasn't even a sun until the 4th day, so how do we even know what the first 3 were? Did a donkey really talk? Did a virgin actually give birth? Did a man rise from the dead? Did God actually say? Of all the books out there that have ever been written, there is one, which is actually a collection of books, that I think we would call the book, and that would be the Bible. And the first deception that we see chronologically in the Bible is Satan saying this to Eve. So you could say this is actually the oldest trick in the book. Why does the devil still do it? And any of you have dogs? You take a dog, it's a ball, their favorite ball, and you go, what does the dog do? Where'd the ball go? Oh, wait, you've got the ball. You come back 3 months later and do it again, is the dog going to be like, no, I'm on to that noise? No, they're going to go running for the ball that you didn't throw. As long as it works, the devil's going to keep doing it. So our job is to say, okay, we should say what Eve should have said. Yes, God did actually say that. And that's good enough for me. Let's pull back a little bit. Let's get a little less technical for a moment. Here's Newton again, just because you can never get enough of Isaac Newton. In the absence of any other proof, the thumb alone would convince me of God's existence. Now, what does he mean by this? What does that mean, the thumb alone? Well, I submit that it means this. It's an expectation, right? If you say the universe is random, everything is a product of just random chance occurrence, and this goes not just for Big Bang cosmology, but this goes into evolutionary theory as well. What do you expect? Now, not necessarily demand, I will grant that, but what do you expect? You might expect a lack of structure. You might expect things to be homogeneous, just to kind of all be the same. You might expect it to be disordered. And you would expect the exact opposite if there was something created. Again, don't demand. There's a lot of modern art out there that you might look at and say that doesn't appear to be created, but it turns out it is. But our expectations, especially with the way that God is formatted in the Bible, we expect to see fine structure. We expect to see diversity. We expect to see order. Here is a beautiful picture of the English countryside. Imagine you are out for a hike, and you come across some edible berries, you eat them, no big deal. There's some foliage that you walk over, and you might trample it under your feet. Not a big deal. We lived in Pennsylvania for a while, which is one of the greenest places in the world. If you trample on some plants, they're probably growing up right behind you as you're walking. If you're out in the wilderness, if you take a machete and hack through a bush or something to make a path, the animals around might thank you. Right? It's not a big deal. But let's say you come upon this, and I chose this image specifically because I didn't see any man-made objects in it. If you do see any man-made objects in it, just ignore them. But I don't think there are any in here. But you still have some things on here that if you came across this on your hike, you would have to say, is this land cultivated? Does it belong to someone? If this land belongs to someone, I need to be careful where I step. If I see edible food, I should probably leave it alone. That might be someone's crops. I shouldn't hack through this hedge and let the cows out into the other field, because someone may have put that there to keep them corralled. So you may look for clues to see, does it actually appear that someone did this on purpose? Did they create this space, so to speak? And you can see the analogy. If the universe is created, that means there is a creator. And if there is a creator, that means that we need to respect his ownership of the creation. If there's not a creator, hack away, eat the fruit, do whatever you're going to do. It doesn't matter. We're just animals. But if there is a creator, we now have an obligation to be respectful of his creation. So there are a lot of systems that can show this. There are a lot of things out there that you can look at and say, does this or does this not look created? And I'm going to leave you guys with my favorite one. The Earth, Moon, Sun system, right? So we have the Earth and we have the Moon. This is what they look like size-wise next to each other. This is their actual relative size. Doesn't show their distance, though. This shows their distance. This is a recent photograph taken by a Chinese probe, which is fantastic. This shows the backside of the moon, and then the Earth illuminated by the sun in the distance. Such a cool shot. But they're very, very far away. Looks like this. This is them to scale and distance to scale. Now, remember, expectations versus reality. If we have an expectation that this is a random universe, the Earth's size relative to the moon is random. The distance there between is also random. But there's one more very interesting body in this system, and that's this guy, the sun. Here's the Earth and the sun relative to one another here. We're right there. Sun's like, I got solar flares bigger than you. That thing would swallow us without missing a beat. And the sun is a lot larger than the Earth, and you can see it has this beautiful corona, this outer edge here of fire that's flaming up there on the surface. This ball of what we believe to be plasma infusion going on here. I think it's, again, a good model of how the sun works, but if someone comes along with something better, that's fine too. And you see the moon there, that little tiny, tiny dot, gives you a little idea of the size. I can't show the distance one because there would be no Earth or moon. They'd be smaller than pixels. Which, by the way, a really cool website called If the Moon Were a Pixel. Check it out sometime if you want to get some idea of the size and scope of our solar system. It's a really fun one. This guy takes the moon, makes it 1 pixel on the diagram, and scales everything to that, and you just end up scrolling for a really long time through empty space for most of it, but it's a fun one. So these all, if we have a random universe, the sun size is, again, random. It's a main sequence star, so there's some parameters for that, but the fact that it's even a main sequence star would, again, be random. Its size relative to the Earth, random. Its distance, random. Its size relative to the moon, all the distances there between, completely random, right? Now, there are certain times where from our vantage point on the Earth, the moon will interpose itself between our view of the sun. It's called a solar eclipse, right? And when that happens, this is what it looks like. This is an actual image taken by an amateur astrophotographer of the moon with a solar eclipse with the sun. And you see that the moon covers the sun so perfectly that you just see that corona and nothing else, which is amazing. It's mind-blowing how perfect that is. It's, to give you an idea, to give you a slight analogy on this, if you're familiar with Epcot Center, it's like this big ball. It's supposed to be like a biosphere or something. I don't know what it is now. It probably just has a ride in it. But it's a big ball with all these pyramids on the outside. So imagine, if you will, for a moment, that you're standing some distance from Epcot Center. How far? Random. Now you take a ball of random size and you throw it a random distance. What is the likelihood that if you line up that ball that you just threw with Epcot, again, all random sizes and distances, and close one eye, that it's going to do this? That it's going to cover it so perfectly that all you'll see are just the bumps from the little pyramids. That doesn't match our expectation at all. It's kind of the opposite of this, right? Our reality is amazing and our expectation wasn't great. Now, before you see it, because there are a lot of great theories out there, right? Think back to that picture of the English Cotswolds, right? If you had some of the smartest people in the world working together for decades to explain why, no, this is not cultivated land, they'd probably come up with some pretty cool theories. Oh, there were these wind eddies, and that deposited these seeds and lines, and that's why we have rows of crops. Okay, I mean, I wouldn't buy it, but sure, there might be some interesting math in there. What if someone were to say, well, maybe it's not random, but maybe it's not special? Maybe there's something having to do with distances and gravities and heavenly bodies that demands that they be at these perfect distances. Well, we don't have to have a model, though. I don't know if you know this, but we are not the only inhabited planet in our solar system. Did you know that? There are several other inhabited planets, one of them being Mars. Okay, it's only inhabited by robots, but it is inhabited by robots we sent there. And one of the robots was there once when Mars's largest moon, Phobos, interposed itself between the Martian surface, where this robot was, where this rover was, and the sun. And so we got to see a Martian solar eclipse, which is so cool. I mean, just think about how long ago it was that the Wright brothers were. You know, we're talking a little over 100 years, and now we're taking pictures of solar eclipses on Mars and sending them back. That's mind-blowing. All right, so you ready to see a Martian solar eclipse? It's not very impressive. I mean, the pictures, it's super cool. You can geek out about this picture, and I do as well, because it's a super cool picture, but this is what our expectations would be if things were random. This is what it would look like. We would expect that it's just a rock that kind of blocks some of the sun. It's cool, it's just not impressive. All right, so let me wrap up with a couple of points here. So we're talking Big Bang. I have a couple of big takeaways that I want you to leave here kind of considering. One of them being, models are not reality. Okay, if someone has given a great model, that doesn't mean that it's real. As a matter of fact, one of the coolest things you can do in physics is overturn a long-standing model. That's like secretly what most physicists want to do, is overturn long-standing models, because that opens up new things. So models are not reality. The evidence doesn't demand the Big Bang. Now, I don't want to be misrepresenting here. There is some evidence that is congruent with the Big Bang cosmological interpretation. There's not nothing. There are some things, like Hubble redshift was one of them. If you say that's expansion, well, if things are expanding, they should have been smaller. There are things like that, but the evidence certainly doesn't demand it. And as a matter of fact, there's a lot of evidence that completely counterindicates it, and you require all sorts of new physics that no one has been able to find to even get it to go. The Bible certainly doesn't teach the Big Bang. Big Bang is not in the Bible. If you allegorize the Bible, if you make it into just this metaphor, it's not there. You have to revert to the Bible simply being mythology. And that's where a lot of people are, too. If you've heard the ANE interpretation, the ancient Near East interpretation, is people essentially saying, well, this was Moses' way of combating the mythology of the ancient Near East. Which doesn't make sense because you're saying, well, he combated it with another mythology that's absolutely untrue. And then the last thing is the finger of God is evident in his creation. And I think that is abundantly clear. You could do a whole talk of just examples, which would actually be a pretty cool talk. But I want to leave you with Romans 1:20 here. For since the creation of the world, his invisible attributes, his eternal power and divine nature, have been clearly seen, how? Being understood through what has been made. So they, and this is the people that say there is no God, are without excuse. And I think that is amply demonstrated here, and there are 1,000 other examples like this. So my point to all this is, yeah, there are a lot of smart people that say this is wrong, but there are holes in those theories. The universe comports with what God has told us. We need to take confidence in God's word, and you can take confidence in God's word. That's what I have for you. Thank you for your time and attention. And I think we do have time for questions. If anyone has questions on anything. Oh, okay. You do your thing.
Is we're going to pass the bucket, not the hat, buckets around, see if we collect enough to at least buy him gas home. And he doesn't live too far, so it's not too bad. But we have books in the back still if you guys are interested in buying books. And if you're interested in... Oh yeah, it's donation only, buy. I mean, basically make a donation, take a book. And if you don't have cash, there's a Venmo sticker in the back, so you can do it, donate that way. Also, if you're interested in hearing it again, because I think I need to hear this about 6 more times.
You're going to whether you need to or not. That's
you can see there's little programs in the back. You can see where he's going to be. And then Mike Riddle is going to be during the days if you're interested in hearing him speak. There's Friday at the library. Is the next one? Yeah.
1 o'clock on
Yeah. And then we're up in Emmett tomorrow. So with that, we'll pass a couple of buckets and see what we get. And thank you guys very much. And this is stump the physics guy.
Oh, that'll be fun.